Hi. In this video I want to talk about memorization in neural networks, talking about what is memorization, does it happen, when does it happen, and also can we see some examples in ChatGPT of memorization. So to start, I will start with defining memorization and talk about whether it might actually be necessary to also memorize when we're trying to learn a good model. And I'll start with this paper, Does Learning Require Memorization? A Short Tale About a Long Tail by Vitaly Feldman. So let me start with the more formal definition that this paper introduces. So in terms of notation, we have this dataset S, which consists of our data points xi's, the input into our models, and some labels yi, and we assume we have small n of those data points. And then what we're trying to measure is essentially the memorization of a particular algorithm on a particular training dataset for a particular choice of data points, in this notation I. And how do we measure it? We essentially kind of say we train two models. One model is trained on the full dataset S, and the other model is trained on the dataset S except for that particular example I for which we want to quantify memorization. And then we look at essentially the difference in predictions that our trained model makes in those two settings. So one setting where the xi itself was part of the training dataset, what's the prediction that it makes then, versus what is the prediction that it makes when this xi was not part of the dataset. And the more different these two would be, the more you could say this particular data point is memorized, since if including it in the trained dataset results in a different label as to not including it, it might mean that we have just memorized this data point. We aren't able to generalize to this data point when we don't include it using the other data points in the trained dataset. So the formulas might make this more clear. So in this notation, H is a certain hypothesis that is generated either from an algorithm sampled, let's say from a random distribution A, obtained when we trained on the full dataset S, and in the second term it's sampled from an A which was trained on the dataset which excluded this particular data point I. And then we look at what is the probability that our hypothesis H, when applied to our data point xi, gives us the correct label yi when this hypothesis comes from the dataset that had xi in it, versus the second term, same thing, prediction of hypothesis H on xi, what's the probability that that is equal to yi when this hypothesis comes from a setting which did not contain a particular data point I. So again, the intuition would be to just measure how much removing a certain point would influence the prediction on that particular point. If it influences it a lot, you could say it has been memorized. If it doesn't influence, the other data points are sufficiently informative to also learn a good label for that particular data point. Now, the first observation, if we dive deeper into this paper that this paper makes, is that real data often has a long tail. So specifically what it mentions in the paper is, it is based on the view that the primary hurdle to learning an accurate model is not the noise inherent in the labels, but rather an insufficient amount of data to predict accurately on rare and atypical instances. And such instances are usually referred in practice as the long tail of the distribution. So first point is that whenever we are working with real-world data, it does have a certain long tail, aka they do exist very many samples which are atypical, rare, and so forth. And then to formalize the notion of having a long tail, this paper says we will model the data distribution of each class as a mixture of distinct subpopulations. And then the example that it gives is, suppose we consider birds. The class birds themselves might also consist of different subpopulations, like different species of birds, different perspectives on the birds, different light conditions in which the birds were photographed. And then in order to formally model this distribution, we say that, or the paper says that we consider each of these subpopulation distributions to also have a very long tail. So point being, data distribution of each class is modeled first of all as a mixture of these different subpopulations, and then the distributions of those subpopulations or their frequencies are very long-tailed. Then, if we read on in the paper, at some point it says a data set of n samples from a long-tailed mixture distribution will have some subpopulations from which just one single example was observed. So, if we still think that this subpopulation is particularly is relevant, we might say, well, to learn something about this subpopulation, we then basically have to memorize that particular example, because there are no other ways to learn something about that particular subpopulation if we just have a single sample, single data point in our trained data set of that particular subpopulation. So that being said, so again, reiterating, if we say that we have subpopulations with just a single example and we want to learn something about that subpopulation, we have to potentially memorize it. Then the question that you can ask is, well, do we actually want to learn it? And this is what the paper also says. The question is whether this is actually necessary for achieving close to optimal generalization error. As the paper says, if the example comes from an extremely rare, or let's say an outlier distribution, then memorizing it might not have any particular benefit. So suppose that in our test data, it's super rare that we will observe another one of these outliers. So you might as well be like, well, who cares? Let's just forget about it. However, at the same time, it's possible that the example comes from a subpopulation with frequency of the order 1 over n, aka it's not that rare of a subpopulation. And when we would look at test data points, so the data points that we don't see during training but on which we still want our model to perform well, we might actually see other data points from that particular subpopulation. So point being, if the example is an outlier, aka some like super rare subpopulation, which we don't actually want to learn because we're like, we'll never see points from this particular distribution, from this particular subpopulation ever again, then you might say we don't need to learn it. But if it's not that rare, yes, we want to learn it because it might actually increase the accuracy for this entire subpopulation whenever we apply our model in real-world data sets or in unseen data. So then comes the main point of this particular work. So let's first read from the paper itself. In addition, having a single representative from a subpopulation can make it impossible for the learning algorithm to tell whether the provided label of that example is accurate. Therefore, an algorithm can only avoid the risk of missing subpopulations with significant frequency by essentially also memorizing examples from these outlier subpopulations and mislabeled examples. So to summarize this, you can say that in order to achieve good accuracy on subpopulations that are not that rare, we also need to memorize outlier subpopulations, because our model essentially during training has no way of distinguishing between the two. It doesn't know, is this an outlier or is this example actually accurate? And to kind of generalize or optimize, let's say, its chances of also predicting well on the test data, which might have more of these not that rare subpopulation data points, it just says, okay, let's just memorize all of them. The same author has a different paper where they also, the paper is very close, but the title is What Neural Networks Memorize and Why, Discovering the Long Tail via Influence Estimation. They also show some examples of data points that have a very high memorization value, so that are actually probably memorized as defined by this particular metric that this work uses. So if we look at the pictures that we have here, so if we look at the top ImageNet data set, where we have this bobsled, the images which have value 0, they are kind of like not memorized at all. So these, you could say that these are relatively standard images on which if we remove one of those images, the prediction on that particular image would not change that much, probably would still classify it correctly. But if we go to the images that have this memorization value of 1, you can actually see also intuitively that these are kind of weird samples. So they're either like with a different background than your typical bobsled, or they have some other weird items in there, the bobsled not being like the main thing. And these are essentially the examples which have a very high memorization index, aka if we remove them from our trained data set and then try to classify them, we might make incorrect predictions. So in order to correct these guys correctly, we need to actually memorize on these data points. And you can kind of repeat the same analysis. Let's look at, for example, the MNIST examples, which is like the right corner, the lower right corner. Again, the examples on the top are relatively nice, 2s, 3s, 5s, and 6. But if you look to the very bottom row, I guess you can still maybe make out that it's a 2, and then there's maybe some 3s next to it, but it's actually relatively vague. Like it could also be, one of them could also easily be a 7 or like a 6 or a 9 or whatever. So again, in order to still get a good accuracy, the model says, okay, I'm just going to memorize these ones because there's no way I can generalize from, let's say, the top images to the bottom ones if I don't actually include them in my dataset, aka if I don't actually memorize them. All right, then there's a second model, which second paper, which I think is very interesting, also related to memorization, but in this case related to memorization in generative models, which is called The Secret Sharer, Evaluating and Testing Unintended Memorization in Neural Networks. So let's look at the abstract first, and then I'll kind of go deeper into what the paper actually discusses. So in the abstract it says, this paper describes a testing methodology for quantitatively assessing the risk that rare or unique training data sequences are, as they call, unintentionally memorized by generative sequence models. So ChatGPT is kind of like a generative model, so that's why this paper is particularly relevant now, I think. And then it goes on to say, in experiments, we show that unintended memorization, which we will define in a little bit, is a persistent, hard to avoid issue that can have serious consequences. So main point of the paper, generative models memorize things that they should not actually be memorizing, or at least there's no point for them to be necessarily memorizing these things. And sometimes this even leads to certain privacy and security risks, as I will show in the next point. So I think this example that the authors have in the very beginning is the one that kind of makes the point very clear. So suppose that users input this phrase, my social security number is ... into like a generative model that then kind of tries to auto-complete this sentence. And suppose that the model actually indeed auto-completes it with a particular social security number. Now, obviously, this would be not great. So point being, certain prompts that we give into our generative model may get completed with what we call secrets, or basically oddly specific details, potentially privacy sensitive details, security breaches, and so forth. The other point that the paper makes is that it's actually relatively hard to prevent this kind of memorization. So as they say, we find unintended memorization to be both commonplace and hard to prevent. In particular, such memorization is not due to overfitting. It occurs early during training and persists across different kinds of models, different kinds of training strategies, and even when the memorized data is very rare and the model size is much smaller than the size of the training data corpus. So it's hard to actually then, once we know models do this, we don't actually know necessarily how to actually protect against these kind of problems. So let me go deeper into what the paper actually discusses. So the setting that they consider are generative models where, in essence, without going into detail on how these models work, but the idea is to estimate this probability P of x1 up to xn, like some sequence of tokens. How likely is it to observe this sequence of tokens? We want to model, estimate this particular distribution. And the main goal of these generative models is basically to just say to probabilistically generate a certain sequence of tokens. And even more rough than that, you can say which, in terms of language, which word is likely to follow a particular set of words. The authors talked about this in the abstract as well, this concept of unintended memorization. So what is unintended memorization? As the paper says, the above suggests a simple definition. unintended memorization occurs when trained neural networks may reveal the presence of out-of-distribution training data, here defined as training data that is in essence irrelevant to the learning task and definitely unhelpful to improving model accuracy, but somehow the network is still memorizing these things. So points being, unintended memorization doesn't improve the model accuracy, seems to be unhelpful and irrelevant to whatever task the model is trying to actually learn. To link it to the previous paper that I discussed, you might actually say, what does it mean unhelpful to the task? Because what the previous paper then said is that we actually need to memorize outliers that might be unhelpful to improving the model accuracy, but also outliers that are actually useful to be learning them, that come from these useful rare subpopulations. So because the model isn't able to distinguish between those two things, it says let's just kind of memorize all outliers, whether good outliers or like useless outliers. So this is just a kind of caveat to this phrase that it's irrelevant to the learning task, unhelpful to improving model accuracy. Based on the previous paper, the two kind of go hand in hand, learning irrelevant features and still rare but relevant ones. Okay, so continuing with this social security example, let's just look at it in a little bit more detail. As the paper says, consider a generative sequence model trained on a text data set used for automated sentence completion. Ideally, even if the training data contained rare but sensitive information about some individual users, the neural network would not memorize this information and would never emit it in a sequence completion. In particular, if the training data happened to contain text written by user A with the prefix "my social security number is ... one would hope that the exact number in the suffix of user A's text would not be predicted as the most likely completion. In other words, if user B would type this text prefix, he would not be able to generate user A's social security number. So hope is we don't memorize rare examples, but this paper wouldn't exist if this were the case. So the point is we do memorize them. How does the paper approach this particular problem? So again, they considered language models. So they train a model on a particular, this Penn tree bank data set. And an interesting thing that they do is basically they say we augment this data set with a single out of distribution sentence. My social security number is 078051120. And then they train their their model, their LSTM, on this augmented training data set until it reaches a very small loss, validation loss. And I try to do this without necessarily overtraining to avoid this argument that, oh, this only happens when you're actually overtraining your model. So then what happens is after asking the model after training giving it a certain partial prefix, will iterative use of the model to find a likely suffix ever yield the complete social security number as a text completion? And then the answer is yes. So in particular, if the initial model input is this text prefix, my social security number is 078, then whatever kind of approach you use to generate the most likely next tokens, it's very likely that you will get the remainder of the inserted digits, so this 051120, and in particular, what they say is, well, whenever 2 to 4 of the first numbers of this social security number that they inserted into their training data set were given as the prompt, then the model would complete the remaining 7 to 5 SSN digits. So that's an issue, obviously. And the crazy thing of this is kind of that you have this massive data set where you've literally just included a single out of distribution sentence. And then when you query it, so when you put in the right prompt, you can actually reconstruct this super rare data point. So these are then the results that the authors have. So some of the results that they have. What they do, just in terms of more detail, they insert the canary near the beginning of this data set, disable shuffling, so that this data point that we inserted, what they call the canary, it occurs at the same point within every epoch that we have. And then figure 7, which is the figure that we have here, shows how unintended memorization begins to occur over the first 3 epochs of training. The way they measure this unintended memorization is through this exposure metric that they discuss also later on in the paper. I won't go into that here, but point is, even early on in training, we are already somehow memorizing this very rare data point, this canary that we inserted into the data set. So the conclusion from this first part is, let's say that we defined memorization as kind of very roughly the change in the prediction on a certain data point, xi, when either I have xi in my trained data set, or the second setting, I have removed xi from my trained data set. If I've memorized it, the prediction will be vastly different. If I haven't memorized it and I'm able to kind of generalize from my trained data set also to my point xi, because it's like a standard data point, then I would not have memorized it. So conclusions from these papers is that yes, neural networks, they memorize data, and specifically this may be actually even necessary to achieve good performance. What are the memorized data points? Well, for example, mostly they are data points that are from relatively rare classes. And the other point was that we had this unintended memorization happen when memorizing a particular data point did not improve model performance. With generative models, when faced with the right prompt, they can generate outputs that are very clearly this example of unintended memorization. So they have memorized, again, very rare data points that in essence by themselves did not seem to improve, like did not even seem related to the task that we're trying to do, but are still clearly memorized, leading to this unintended memorization issue that generative models have. Okay, so then I went on to the ChatGPT stuff to see whether it can give me any kind of guidance as to whether it has memorized certain things. Now, obviously, this distinction between memorization it's not necessarily very easy to make it when you're not able to actually retrain a model with and without that particular data point. And the definition of memorization itself, you can say it's kind of vague. Because when is it unintended memorization? Okay, when is it supposedly not relevant to the main task versus when is it actually relevant to the main task? But in any case, I just wanted to know, is ChatGPT able to, let's say, answer with very specific data or outputs that I'm pretty sure would not have been a massive part of their training data set. So this is the way I'm kind of defining memorization now. I'm asking it relatively rare information that even if it has it in its trained data space, it would be really rare. And then I'm wondering, can it actually reconstruct those particular data points? Okay, so what did I start with? I just started asking the guy whether it was familiar with this WaveNet architecture for financial time series forecasting. Why? Because I worked on that. And I'm trying to obviously kind of get it to say sensitive information about myself. So that's why I'm warming it up with asking it whether it knows this one particular paper that I worked on, which is already kind of like a rare data point by itself. So it says, yes, I'm familiar with WaveNet architecture, including its applications in financial time series forecasting, blah, blah. It's a network that uses convolutional layers, and so forth, and so forth. Great. So then I asked it, can you give a reference that uses WaveNet for finance? And then it's happy to do so. So it says, okay, certainly here are a few references that use WaveNet for financial time series forecasting. None of them are by me, which is slightly disappointing because I thought I had a good paper in that area. But I'm sure all these other ones are very good too, if they even exist. Because as I'll show you later, it generates random stuff. So then I go on and ask it, well, do you actually know anything about Anastasia? Me. And then it made up something completely random. So it said, okay, yes, she's a data scientist and machine learning practitioner who has published research in the areas of deep learning, reinforcement learning, and apparently I'm the author of the book Machine Learning for Finance, Principles and Practice for Financial Insiders, which is interesting because I did not even know that I had apparently already authored a book. Even more funny than this is that when I started asking ChatGPT who I was without starting with these prompts of like, oh, do you know financial time series forecasting? Do you know machine learning? The answer that it gave me is, I'm sorry, I don't have any information about a person named Anastasia. So it didn't know me when I directly asked it, do you know something about, again, I'm a rare data point because I'm not much on the internet, I think. And it didn't know, but when I again asked him to say something about me after I had queried it with these other questions about financial time series forecasting, machine learning, and so forth, it suddenly did know who I was, and he made me an author of a book. Okay, so let's see what else it has to say. I asked it then, what is your current position then? Again, what am I trying to do here? I'm trying to get ChatGPT to say something that is essentially rare. Even if it knows what my current position is, it's going to be almost memorization, because I'm pretty sure the only place that it says it is on my LinkedIn and maybe on the webpage of the university or something. But that's literally two places which, in the massive data sets that ChatGPT has, I can say is pretty rare. Okay, so here comes another funny thing. I asked it, okay, what is your current position then? Well, he says, honestly, I don't know, as my cutoff date of like my training data is in 2021. So I don't know right now. But before that, she was a, let's see what it says. As of 2021, Anastasia was a data scientist and researcher with expertise in deep learning and finance. Thank you. She was also the head of research at a Hong Kong-based startup, Trading Gene, which focuses on applying machine learning to algorithmic trading. Now, interesting, but this company doesn't even exist, because a quick Google search showed me that it doesn't exist. And even if it does, it's definitely not based in Hong Kong, and it doesn't seem to be doing necessarily machine learning trading. It's more like focused on something with cryptocurrencies. So okay, I say, okay, give me some proof of your statements. Can you give me the link of my LinkedIn page where this particular position is set? Again, because I thought if it can give me a link, it would be an obvious example of this memorization. Now, it did not give me a link. It says, I'm sorry, as an AI language model, I don't have the ability to access the internet or browse websites. However, just search or by yourself on LinkedIn. Okay, fine. Okay. Then I started questioning it a little bit more. And I say, okay, well, I did your advice. I checked her profile, but she is a professor and there does not seem to exist this company, Trading Gene. And then ChatGPT does what we've probably already seen it do. It kind of apologizes for the mistake that it makes, and then it regenerates a certain answer, which does not necessarily make more sense than whatever it said before, because it's still like, well, up to my best knowledge, up to 2021, she was head of research at Trading Gene. Trying to get it to generate something that is relatively rare. Again, like if it can name a title of one of my papers. So I ask it, can you name one of her papers? And it hasn't memorized again, because it just kind of makes up another title, which says that it doesn't necessarily memorize any of my works. Again, slightly disappointing for myself, but it just kind of probabilistically generates a likely title based on its current information that I'm a researcher in machine learning and blah, blah, an expert in time series finance, whatever. So this is not an example of memorization, but this is really would be just like an example of the generative model at work, like literally just filling in the next token based on whatever is likely to follow. Deep learning is likely to follow deep, time series is likely to be followed with analysis, and so forth. Okay, I start to make my prompts more specific, because based on also this paper that we saw, the secret sharer, I then think, okay, maybe if I give it a sufficiently specific prompt, it's going to be able to fill it in correctly. It's not, still no memorization, because when I asked him, do you know any of her papers in the field of option pricing, for example, something starting with a neural network-based framework for financial, and then he says yes, a neural network-based framework for financial option pricing in the Journal of Risk and Financial Management. That's not correct. That's not my paper. So again, no memorization, just random things. I asked it some more stuff. I asked it, do you have any memory of Anastasia working at university? No. Well, now, yes. She has held several academic positions through her career. Apparently, I received my PhD in physics and mathematics. I never studied physics, so that's great. From the Moscow Institute of Physics and Technology. I did not study there. I studied in the Netherlands, but because my name is apparently Russian, this is kind of the most likely thing that this model generates. But points being, still no memorization. It also said that I studied at EPFL, which is pretty cool. I didn't, but pretty cool place. Then I asked, so you're not aware of her doing a PhD in Italy? Again, me doing a PhD in Italy would probably be only found on like literally one place on my LinkedIn profile, which is where it says that I did a PhD in the University of Bologna. So I'm wondering, did it memorize it? Still no memorization, because it answers saying, based on the information available in my knowledge, she did her PhD in physics and mathematics from the Moscow Institute of Physics and Technology. Okay. So I asked it some more of these questions. I asked it, do you have any recollection of someone with this surname participating in figure skating? Because I also did figure skating. Again, I did it very many years ago, so probably just one data point on the internet that would contain it. It still doesn't know. There's no memorization. I asked it whether he knows I studied at the Technical University of Delft. He doesn't know either. So still no memorization. I asked it whether I have any collaborators whose first name is Cornelis. I worked with Cornelis Oosterlee, professor now at the University of Utrecht. But he says I'm not sure of any of her collaborators, but in my database there's no one she's collaborating with by the name of Cornelis. So again, still no memorization. And then I hit kind of the jackpot in this particular video. I asked it, what about someone named Sander? So again, I have 2 papers with Sander. I have way more papers with Cornelis, but somehow now it worked, because it said, let's see, I do have information in my database about her collaborating with someone named Sander Boté. Sander Boté is a researcher at the Centrum of Wiskunde and Informatica in the Netherlands, which is correct. And actually this is kind of memorization, because I literally have 2 papers with Sander. I think 2. And it was able to recollect it, so fill it in when I just queried the first name. It was able to fill in the second name completely correctly. And then even more, he knew who Sander Boté was, which makes sense because Sander is a lot more famous than me. But so maybe that particular part is not memorization, but at least me having collaborated with Sander, I could say it's kind of an example of memorization. And then I found some more interesting things. I asked it, who else have I collaborated with? Then it again made up a lot of Russian names, people that are not actually even existing researchers, at least not all of them, not the ones that I Googled, which is very creative of this algorithm. Again, also very interesting that it just generates Russian names based on my name. I asked it, well, does she have any collaborators in the Netherlands? So again, I gave it a relatively specific prompt, so that it kind of becomes more, it goes in the right direction of potentially finding some kind of memorization in its database. And then it said me this, okay, she's worked with Sander Boté, correct, we already saw it before. Christian Meijer, I do not know, or I have not worked with Christian Meijer. But then it said also Leg Krzelak, and Leg is someone that I've worked with, probably also maybe either 1 or 2 papers we have together, which is definitely also kind of an example of a little bit of memorization, because it's a super specific name, and it does correctly generate that I worked with it. Again, Leg is a great researcher, so there's probably a lot of papers, videos, everything out there of his work, but the fact, so that would not knowing who he is would not be memorization, but just the fact that he is my collaborator in the Netherlands, I can say it's a little bit like memorization, as it's a very rare data point in, a relatively rare data point, at least in this massive data set that ChatGPT was trained on. So that's it. Thank you very much.